Hi everybody, we're now on our next video in NetLogo in Mathematics in Modern World. That is where I'm showing you guys about fractals. So let's continue with this L-System Fractals. We'll put the Mandelbrot set in the last part, since it's created by Benoit Mandelbrot, the father of fractal geometry. Let's start with this L-System Fractals. What are these? This program draws special types of pictures called fractals. A fractal is a shape that is self-similar. That is, it looks the same no matter how closely you zoom in or out of it. For instance, a tree can be thought of as a fractal, since if you look at the tree as a whole, you see a stick, that is to say the trunk, with branches coming out of it. Then if you look at a smaller portion of it, say a branch, you see a small similar thing, namely a stick with branches coming out of it. So these are fractals. So LSystem Fractals let us see these different kinds in this NetLogo library. So for instance, we want to click on the swirl, press the buttons to set up examples of L-System Fractals, then press go or go once buttons. So I'll click on the swirl and I'll make use of only one color for us not to get confused. I'll click go once. Anyways, let's do that again. Color rather here. So I'll go once. This is a swirl fractal. As you can see, it's becoming more dense and dense. But the thing is, it's swirling in such a way that it is self-similar actually. If we're going to zoom that in, say you want to have some colors with it, 9 colors, it will look like this. There. Okay. So it will continue on and on and on until it will be very, very, very dense. So that's a swirl. A ball is something like this, similar to the swirl, but not close enough, but not exactly the same. It's really rotating itself. Again, it does something like this. Okay, and then spread, 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 and then it will eventually spread all across the parts until you cannot see any parts no more. Which is of course of the denseness of the lines. Let's try for the tree. It's still ongoing actually. I think we have already seen this. It is a tree simple in our previous video. Okay, so if we continue drawing that, it will create a tree. Notice that the parts here are continued from here, so this is an error for the codes. Tree 2 will be something like this. You have a Y, and then this Y at the parts of the edges of the Y, you create another Y. So if you go and reiterate this, it does like this. You do that again and 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 again. So that is a tree fractal also. It's not so good though because it's reflecting, you see. So we have only one color. It looks like this. Okay, right? Brilliant, isn't it? Okay, so that's a tree fractal. Next is the Serinsky tree. Okay, so if it will look like this. Let's make use of less colors. We have faced this already. This is also known as the Serinsky triangle or the Serinsky tree in this matter. Okay, and then let's try the figure 8 covering. What does it look like? It looks like this. Here, here. Okay. So what is happening here is in every. Okay, it's lagging now. You go once. Rather, let's make it one color. You go once. You create a cross. Okay, and then on that parts of the cross, you create more crosses there, just like that, and then you continue with this process, so on and so forth. There. So this looks like now this looks like a diamond, a square, but actually it's quite not. The fractals, as we all know, have fractal dimensions. So it's not the second degree, it's not also the third degree, but it's somewhere in between the second and the third degree. Okay, so that's figure 8 covering, and then we'll have of course the Coke snowflake. We have faced this in the first video. Only that it's now having the plane as it is. It's not only not only on the x-axis. So if we're going to have only zero color to look like this. So in every edge, there's a triangle popping up, and then triangle, and then you continue with that process with that iteration, and then voila, what you'll have is the Coke snowflake. Okay, so in this NetLogo model, we have seen 7 examples of L-System Fractals. That is namely the swirl. Okay, we have the swirl, and then we have the ball, then we have the tree, we have the tree 2 and tree 1. We have the Serpinski tree or the Serpinski triangle. We have the figure 8 covering, and then we have here the Coke's snowflake. There. So it's quite laggy if we're going to if I'm going to continue with that. Okay, let's have the last fractal that we have here in the fractals models in the NetLogo. We'll have the Mandelbrot set. So this model draws a mathematical object called the Mandelbrot set, named after its discoverer, Benoit Mandelbrot. It demonstrates an interesting technique for generating the design as well as providing a nice example of hill climbing. So let's have it here. So number of turtles, let's set it up. Okay, so these are the turtles. What it will have is that we're going to have we have this function, this iteration function in the Mandelbrot set, which the Mandelbrot set follows. This is like a collection of all the Julia sets out there. If you know Julia sets, it's named after a mathematician, Julia. And what Benoit Mandelbrot did is that he collected all the families of these Julia sets and create a unified function, and then what you'll have is the Mandelbrot set. So if I'm going to click go, what the turtles are doing is that it's bouncing. It's trying to create um a set um um using this function, okay, and trying to put all the possible answers there. So if we're going to continue this, actually it will create something like a set or an image. Okay, so let's stop that. Let's set up. Let's make it faster. Maybe this one. Maybe my computer cannot handle it. So let's click go. What it will do is like this. Maybe even faster. Okay, there. So you can see it should be moving, but it's slowing down because of the computer. That is now what we're seeing is a start for the Mandelbrot set. Okay. So what will happen here in this part here in this purple, red, green part, all of this part will be black. Okay, and everything here on the edge is where the interesting part is. As you zoom in that part of the edges of the circumference of this Mandelbrot set, things get very, very interesting. So if we're going to zoom that in, you will see intricate colors. Depends. The colors actually tells you how many bounces you have until you go out to jump out of the outside the function. So this is set. We are already in the how many 5,600, 5,800 iterations, and you can see so far that the set is now being complete. The violet part there is starting to become what, something like blue. But the tell is that when you have the violet part there, meaning it's a solution to the function, and then so on. Okay, I think it will take a lot of time to really finish this. But the thing is, you got the point. So, this is the Mandelbrot set created by Benoit Mandelbrot, and then it is the one function or the one set that started fractal geometry, and of course, the main motivation or the main inspiration of Benoit Mandelbrot to create his book Fractal Geometry of Nature. Okay. So that's the Mandelbrot set. I think all of the fractal models here in NetLogo have been tried by us. So the Coke curve in the first video, Sierpinski simple or Sierpinski triangle, the star fractal, and the tree simple are all there in the first video. This video we have talked about the L-Systems Fractals, which are 7 of them, and the Mandelbrot Set, which is over here. Okay, so that's it for this video. Thank you very much for watching. Hope you like and subscribe, and see you in the next following videos. Okay, so thank you very much.